For the first week of August, we are facing this problem, and this year also we are facing such problems. But these two incidents, due to this heavy rain, this plane crash, and also Rajamala landslide, it shocked us, and we would like to express our condolence, early condolence, in the name of UL Space Club to those people who died in those accidents, and we should pray for them. We should work for them. What we can do, I don't know how much we can do for them, but we should do with what you have. We should. And welcome to the program. And when I talk about the speaker of today's program, I don't want to welcome him because he's a regular member. He's one of the brilliant fellow of UL Space Club, Bharath Sreejith. I just want to welcome him formally. Welcome, Bharat, and two panelists also are there. Two brilliant panelists we got today. And Bharat is going to speak about black holes and so black. That's his topic, and we can go to the secrets of black hole with his talk. And I invite Shahil sir to include more points, and welcome the chief panelists and our speaker to this program. Shahil sir.
Thank you, Varun. We all sit in our house safely, but a lot of people are in rain and in trouble now in Kerala and all over India. And today, when we start our 12th webinar here, we have to remember about them. Because a lot of people are toiling there in the midst of this COVID. In Calicut, all the hospitals are filled with the wounded personalities. Yesterday night was a very dreadful for us, and today there was a thinking also from our part whether to start or continue with our webinar like that. A very sad moment for us, and we are also part with those injured and the victims of these two great or the great loss to our state. And along with that, today we have a wonderful day and a good day for us, because our young blood is presenting a topic very bravely to the scientists of India and the students of India and the scholars and common people of India. We choose the language English here because of this webinar is viewed by a lot of people outside Kerala, and that's why we are presenting it in this way. And we have a lot of scientists, lot of eminent personalities from ISRO, and some common men and professors and some students also with us. And we are very happy to say that it's 12th webinar we are presenting here, and all the 11 were presented by some of the eminent scientists of India. And in all these webinars, there is a very shining star. That is our Bharat, Master Bharat. He is from Vadagara. He is studying in Memunda Higher Secondary School. It's a rural school in Kozhikode district. But that school is having some history in all the academic events in Kozhikode and even in Kerala. And we can say he is proudly say that he is part of UL Space Club and UL Education Program. And he is an all-rounder. He knows everything. That is proved by getting National Talent Search examination. That's an all-over India competition for the students, and he crossed that. And now he is sitting there with his full marks in the +1. Now he's in +2, and we have good expectation on this young, brilliant student. And he's also part of our UL Space Club. UL Space Club started its journey 4 years back under the leadership of E.K. Kuttisar and Uralangal Labour Contract Society. And we are continuing that journey. And this pandemic made us to do this kind of webinar. And I am saying, I'm repeatedly saying these things for the new entrants and new guests to our webinar. And today he is speaking on the most enigmatic theme of black hole. I think it is a wonderful thing, and still it's a part of an enigma. It is not clear, and even there was a report from NASA last year. They captured a picture of black hole by assembling some of its parts, and that was presented to the students. And all the students are curious to know what is black hole. As today's topic is so hot and so interesting, we cross 100. The today's participants is more than 100, and we expect that we raised up to 200. And that's because of the star and the great charming star that is Bharat, and he is so well known in all over India in the science community and all the student community. And I welcome our proud and precious Bharat to this forum officially, and to deliver his webinar on his favorite topic on black hole, because he want to become a physicist, especially a theoretical physicist, and to conduct his studies and research on that and live for that science community rather than gaining money or securing a good job in some other places. He want to serve our nation and to guide our students. That much of ambition is with him, and we can say that he will accomplish that. And today, in support of his and to bless him, we present two eminent professors or the academicians, what I say, the masters of science, to this forum. The first one is Dr. N. Shaji, former HOD of Maharajas College, Ernakulam. But rather than saying that he is former HOD, we can say he was part of Institute of Mathematical Science, Chennai, from where he has taken his PhD, and he was a close associate of Dr. E.C.G. Sudarshan. He was the director of that institute when he was taking that PhD, and he's also blessed with that. And now he is working as a faculty in CUSAT, and moreover that he is the vice president of the major science organization in Kerala and India, that is Kerala Shastra Sahitya Parishad, and he is conducting lot of classes all over Kerala and outside Kerala, and he is all-time a living all-time teacher, and he is usually take class to students, college students, school students, and even to the common man, and that he's proved in his life and simplicity. I have known his all these records from some other friends and some other sources. He didn't reveal me that these kind of things are with these great persons. And we can say Dr. Shaji sir is an apt person to bless our master Bharat and to guide him in future for his future studies also. A warm welcome to our respected N. Shaji sir to our forum. Welcome, sir.
Thank you.
Yes, sir. Next, our next panelist is Dr. P.S. Shoban. He is always with us. When we started our journey in the month of May, he was with us, and he was actively participating all our webinars, and he is supporting us with all his sources. Dr. Shoban sir is the man who linked this great person Shaji sir to this forum, and that's why we all are blessed with the presence of Dr. N. Shaji sir because of Shoban sir. Shoban sir is also already introduced us, and he is taking part a major role in the educational field of Kerala, and he was a professor in Maharajas College. Along with that, he is engaged with a lot of educational activities in the schools, college, and to the common man, and he's also a good science student, in my view. A warm welcome to our beloved Shoban sir to this forum again. And I welcome all the scientists and other distinguished guests of our UL Space Club who are participating in this webinar from sitting in different rooms in all different various parts of India. A warm welcome to all again to this program. Your blessing make this webinar more interesting and useful to the students. That's why we are getting a lot of responses to the public. And a warm welcome to all. And our Kuti sir is here. He is the chief patron and mentor of this space club. And we have T. Damodaran sir and all of you are welcome. And along with that, lot of students are viewing this, and all students, teachers, all others and join here are. We welcome you all to this evening, and I invite our beloved Bharath Sreejith to present his story on black holes here. Welcome, Bharath.
Thank you, Shajit sir. Thank you so much for that introduction. In fact, I'm not such a great person as he talked about. I'm only a 12th standard student. He said that I'm a 12th standard student from Memunda Higher Secondary School, Vatakara, Kozhikode, Kerala. Because I have to say that because there are a lot of people from outside Kerala here as well. Shajit sir, can you please tell me if I'm perfectly audible?
Yes, okay.
Okay, so let me start my presentation. Before we begin, let me share my hearty condolences to the victims of the double disaster that happened to Kerala state yesterday. Please do wait, let me share my presentation. Share. Okay. So, Shajit sir, is it visible right now? Hello, Shajit sir. Please do tell me if it's visible.
Yes, it's okay. It's okay.
Okay. So you may not be able to see my head right now because I'm using two devices. Sometimes you would only see this presentation only. So let me see if I can switch on my camera sometimes as well, because I want to show a demonstration in the middle as well. So let me go to my presentation. Okay, Shajit sir, can I start?
Yes, it's okay.
So, good evening, everybody. My name is Bharat. I'm a 12th standard student. As you may have noticed, our session today is about black holes. But we're only going to deal with the basics, some things that you may already know about them. So, in further sessions in the future, we could try more advanced sessions. But for the time being, consider this as an introduction to the most fascinating objects we think we know about, which is black holes. And hopefully, if I don't mess up this session, you could see me once again with a more advanced talk as well. In fact, taking up such a topic is itself pretty much like suicide, because whenever we think about black holes, we reach this whole new world of fantasies and imaginations. And you kids watching right now are the best in the business. So the sort of questions that will come from you in the question and answer session will be extremely difficult for me to answer myself. So I am extremely relieved and happy to have two great physics professors from Maharaja's College, Dr. Shobhan PS and Dr. N. Balaji, here as my panelists.
Hello.
Is there a problem? Okay, let me continue. In fact, I'm honored as well. So I'm sure they'll come to my rescue, come hell or high water. To speak of, I'm not the first student speaker here. Two of my seniors, Master Abdul PS and Master Ashik Yusuf, already. So if you haven't attended them, you could watch on our YouTube channel or our Facebook page, and the link will be given to you in the chat box by Varun very soon. I am actually the third student speaker only, and I hope the saying "third time's the charm" will be maybe true. Anyway, Ashika had already spoken about time travel and special theory of relativity. So we'll build upon that and speak of the general theory of relativity and, well, black holes. Now, there is a fundamental question. What are black holes? A lot of people think they are black objects, huge black spheres with super strong gravity that not even light can escape, and we see them as black. But are black holes that simple? Maybe not. Black holes ain't so black. Yeah, black holes really are the most inexplicable, incomprehensible things that we think we know of. To give you a better idea, black holes are even more incomprehensible than my handwriting. Yes, that is true. So what I'll try to do is to uncover that vial of darkness that surrounds a black hole and tell you of what black holes really are, how are black holes formed, what is the structure of a black hole, how do you observe a black hole, what happens when you fall into a black hole, what if the sun was a black hole, are black holes like Axe deodorant or will they fade away? And most importantly, do black holes even exist? Yes, that is a funny question, but that is the most important one which you will understand. Very well then, fasten your seatbelts because believe me, we are going on a ride to a very hostile environment. Let's begin with our first question. What is a black hole? Well, a black hole is a region in space where a huge amount of mass and matter has been compressed into such a tiny point in space that the density and the gravitational force thus exerted is so strong that not even light can escape from it. So since light cannot escape from it, it would be, well, invisible. A person who has studied the classical physics of gravitation, well, as per Newton's law of universal gravitation, we know the equation for gravitational force is given by F equals the universal gravitational constant times the product of the mass of the bodies over the square of the distance between them. What if the mass of one of those bodies was to be zero? Well, the gravitational force would be zero as well. So you can argue, what is the mass of light? Well, if you take the mass of light as zero, what would be the force of gravitation on light? Well, wouldn't it be zero? If so, how can a black hole even suck in light? The answer to this question was given by the greatest physicist the world has seen since Newton himself. Well, who else but Albert Einstein? When Einstein introduced the special theory of relativity in 1905, many scientists around the world were not willing to accept as it seemed to them as so wild and radical. Many said, this man is not even a working scientist. He's just a patent clerk. Isaac Newton has been correct for hundreds of years. So how can this patent clerk just come out of nowhere and say that he's wrong? Many politicians even insulted his religious inheritance by calling his work as Jewish science, like a way to subvert traditional culture and thinking. But even then, special relativity was yet a big game changer. Till then, we thought that time was absolute and that space and time are two different entities. But Einstein said, wait a minute, is not absolute, time is relative. Space and time are two, they together form what is called space-time. Now, Ashika has already spoken about space-time and he's beautifully explained how to draw a space-time graph and how to represent an event in a space-time graph. So let's probably not go into all that. If you haven't watched them, you can go and watch them from the YouTube channel or Facebook page. But even then, Einstein was not happy with this theory because it could not be applied to accelerating reference frames. Like, for instance, if gravity was present. But Einstein was known for his great imagination. One day, as legend says it, while observing a window cleaner on a ladder near his patent office, he had one of his most famous thought experiments that would go on to change the course of scientific history. Now, he imagined what would happen if the worker was to fall down. Yep, Einstein is a really cruel man. I really don't fancy the idea of seeing a splattered brain on the floor. But that's the way we think. But Einstein did not think that way. He put himself in the position of the worker. So he thought, what would happen if he was to fall down? Well, we're not talking about him hitting the ground when he's falling down. So when he falls down, the only force acting on him is the force of gravity, which will accelerate him at 9.8 meters per second squared, which is the value of acceleration due to gravity near the surface of the earth. And since there is no ground pushing him upwards, well, he would feel no weight. And if there is no air resistance, you can say that he's in free fall, which is basically the same as floating around in free space as the images that I've shown in the slide over here. So in a way, gravity and acceleration but two different ways to describe the same thing. And the thing with Einstein is how he connected gravity and acceleration to produce the greatest theory, one of the two greatest theories that arose in the world in the 20th century, which is the general theory of relativity. Now, think of it this way. Einstein thought, what if he was to be in a room with all the windows closed? You can't go out or come in. Everything is closed. It's a dark room, or yeah, maybe there is some LED bulbs or something. Just don't mind that. So he's in a room. It is closed, and it is on the surface of the Earth. Well, the Earth would attract him at the force which is equal to his weight, that is mg. And suppose let's take his weight as 70 kilogram weight. Okay, let's assume it as 70 kilogram weight. So since he's not going downwards, the Earth would actually be exerting an equal force which is equal to 70 kilogram weight. Now, what if he keeps a weighing machine, a weighing scale underneath his foot? Well, since he's not accelerating downwards, well, it'll read as 70 kilogram weight, which is equal to the man's weight. Let's consider it as Einstein anyway. So then he thought, what if this room was on a spaceship? Now understand, the spaceship is not near this near the Earth or anything. There's no massive body which influences into gravity. It is in free space. There's no sort of gravity, and it is accelerating upwards at a rate of 9.8 meters per second, which is exactly equal to the value of acceleration due to gravity near the surface of the Earth. So what would happen? Well, the spaceship would push him upwards at the rate of m 9.8 meters per second, which is the acceleration. So the force applied on him will be equal to his weight. Similarly, if he was to keep a weighing machine underneath his foot, well, this man would apply an equal reaction force on this, what do you call it, on this weighing scale, which is equal to his weight, that is 70 kilogram weight. So in both places, what we find is that, well, they seem to be pretty similar, because if the acceleration of the room inside would actually feel indistinguishable from being on Earth, because you would only feel 1g, which is equal to the weight of the person. So if he did not know that he was inside a spaceship, he could just as well presume that he was on Earth. There would be no way to tell the difference. But would there? Einstein thought of whether if there could be a difference. So he thought he was inside the room on this spaceship going upwards, and he lit a flashlight, or maybe a laser, let's say a flashlight, from one side to the opposite wall. Well, what would happen? We know that the speed of light is finite. So by the time light reaches the other end, the spacecraft would have moved a little bit up. So if Einstein was to use a very sensitive measuring instrument, he would see that the light actually bends a little bit. Now, what if the same experiment was to be done on the room on the surface of the Earth? Well, we think it's common sense. It would just go straight. There's no problem. But Einstein thought maybe not, because if it did go straight, it would violate the principle of equivalence, as the acceleration of the room in a spaceship accelerating upwards is similar to the effect of gravity on Earth. So light may bend in the presence of a gravitational field. But how is that even possible? Well, light takes the shortest distance from one point to another, and we know that the shortest distance from one point to another is a straight line. How is that even possible? And then Einstein thought, well, what if the shortest path is not a straight line? That was the game changer. Now, think of it this way. We know that the Earth is a sphere, not a sphere, it is more of an oblate spheroid. So if I was to walk from one place on the Earth to another, and if I was limited to the surface of the Earth, the shortest path I can take will be a curved path. Now, if we consider the surface of the Earth as a two-dimensional plane, what I'm doing is I'm only taking a straight line. But since the surface itself is curved, the path that I take becomes a little bit curved. Now, I would like to show you a little demonstration. Can I please switch off this presentation, and can you please look at me for a while? Shadi sir, can you please respond?
It's okay. It's okay.
Okay, so I'm going to show something. Gosh, I have this. I'm switching.
Now the presentation has gone.
Yeah, I switched off the presentation, sir. So I think there is some problem here. Can you see my face right now?
Yes, your face is so pleasing face.
So I have a paper, a flat piece of paper in my hand. So suppose an ant was to walk on top of this paper from here to here. Well, obviously, if the paper is straight, we would see that the ant is walking along a straight line. But what if I take this paper and I bend it into something like a cylinder? Wait a minute, the bending process is taking a little bit longer than I thought. So here, what if I bend it in a cylinder? Well, the ant would still travel in a straight line, but since the surface or the paper on which it is walking is bent, we would see that the ant is taking a curved path. So what gravity can do is that gravity can bend space-time, gravity can crush space-time, and gravity can tear space-time apart. Now, let me go back to my presentation. Wait for a moment. Coming back. Chandrasekhar, please do tell me when it is on.
Okay, it's coming. No problem. You can proceed. You can proceed with the presentation.
It's coming. Okay, now it's fine, right?
Yes. You expand it. Okay, very good.
Okay, now it's fine. There you go. Now let's put it all together. Let's say that space-time is nice and flat. Sir, is there any problem with the audio? I think there is someone trying to speak.
Oh, okay. Gina Rani. Request Gina Rani to mute your microphone. Otherwise, I'll mute.
Okay. So let's put it all together. Let's consider space-time to be nice and flat. Now, there's one problem. Space-time is not exactly flat anyway. This thing that I'm going to show you, this trampoline analogy that I'm going to show you, is only an analogy for visualization. You could actually see it in a three-dimensional place, but since that is very difficult to simulate in a two-dimensional surface or a screen, I'm trying to show it in a two-dimensional plane. So let's consider space-time to be nice and flat and really uniform if there is no mass nearby. But if you keep a massive body like the sun, for instance, what would happen? Well, the sun would curve the space-time around it. It would bend it, creating a depression or something, which you could well call a gravity well. So if light was to pass near it, what would happen is that the shortest path itself, the space-time on which light travels itself is curved. So light would take a curved path. Now, what if I was to keep a body, a massive body, stationary near the gravitational well? Well, it would just fall down, right? What if I give a tangential velocity, a critical tangential velocity, like I push this body? You see some Earth-like blue dot over there. What if I was to push that dot? Well, obviously, it wants to travel straight, but since the gravity well is bent, it would start to orbit around this gravity well. This is exactly what happens when the Earth moves around the sun as per the general theory of relativity. This is also the way the moon moves around the Earth. But there is a problem. You know, the sun and the Earth create their own gravity wells. So actually they have to orbit around each other, right? So the net effect will that they will actually move around the center of mass of the Earth and the sun, which is called the Bary Center. If you were to consider the whole solar system, a lot of people think that every planet orbits around the sun, but that is not true. The sun and every planet actually orbits around the center of mass of the solar system, called the Bary Center of the solar system. In fact, the Bary Center is also fluctuating because when the Jupiter and Saturn actually move to different sites, there is a little problem. Now, Varun will post a link on the chat box after this after this video is over. You check out that link and understand how the Bary Center is influencing the motion of the planets and the sun around the solar system. Now, coming back to our gravity well concept. If you visit centers like the Regional Science Center and Planetarium Kozhikode, or even some other science museum, you might have seen this exhibit called a gravity well. So what you get is something like a funnel kind of thing. There's a hole in the middle, and you have some balls. If you keep the ball over there, it will just roll down into the hole. But if you give it a nice little push, it will start to move around the hole. Now, because of friction, it will obviously lose velocity and slow down and fall into the hole. But when you consider the Earth and the Sun, since there's no frictional force, we don't have to be worried about the Earth falling into the Sun anytime soon. From all this, that is basically what general relativity tells. So you see this equation that the space-time curvature is equal to the stress from the stuff in space-time minus the stress from empty space-time itself. If you don't understand it, don't worry. John Wheeler, a physicist, put or summarized it, the whole theory, in 12 simple words. Space-time tells matter how to move, and matter tells space-time how to curve. That's it. That's general relativity in a nutshell. Now, to prove this theory, this has to make some predictions which couldn't be solved by the Newtonian theory. The first big hit was with the explanation of the precision of the orbit of Mercury. Now, you know that all the planets orbit around the sun, so they travel in elliptical orbits, and well, they are stable elliptical orbits. But the problem with Mercury is that when Mercury travels around the sun, the farthest place or the farthest point at which Mercury is from the sun, which is called the apohelion, actually tilts a little bit. So what you see in this GIF image that is shown in this slide is that the Mercury is moving around an ellipse, but the ellipse itself is moving around a hinge. This could not be solved by using Newton's theory, but when you applied Einstein's theory of relativity here, the results were exactly matching so that it could completely solve this anomaly. But even then, many scientists still doubted Einstein's theory. It took 4 years to give a solid evidence for the general theory of relativity when a team led by English astronomer Arthur Eddington photographed stars during a total solar eclipse. Now, we can, when you look at stars in the sky, you can predict where it will be at any time of the day. But what they found was that when they looked at the star near the sun, it was found to be apparently shifted to a different position from the actual predicted position. Now, how do you even solve that? There, relativity came to the rescue. Now, as Einstein said that space-time can curve, mass can curve space-time, so light would actually be curved by a massive object like the sun. So we can try to explain it with this figure. Well, the actual star, from the actual star, the light actually moves in a different direction, but when it nears the sun, it bends, reaches us. So we know that we only observe something when a light comes from that object, if it is reflected or if it emits the light. So, and we assume that light travels straight. So when light comes like this, we assume that the observed star is actually straight, but the exact position of the star is not straight. It is actually an apparently different position. So since Newton could not solve that, a solid evidence of Einstein's theory of relativity. But you may ask one question. No, sorry, before that, look at this image. This is a beautiful explanation of this effect. It is called gravitational lensing. This process that I call here, that light can bend around a massive object, is called gravitational lensing. This image that you can see is taken by the Hubble Space Telescope of NASA, and you can see a blue smear around well, something like a yellow or red elliptical galaxy. So the real thing is that there is a blue galaxy which is behind the red or yellow elliptical galaxy. So what happens is that the gravitational force of the yellow galaxy which is in front is so strong that it warps the light coming from the blue galaxy, and it appears something like a funhouse mirror, a circle around the yellow galaxy which is in front of it. Now you may ask a question. Well, I understand this curvature of space. Why do we call it space-time curvature? How does time come into the picture? Now think of it this way. Suppose I was to travel from a point A to B, which is a little bit farther away from the Earth. So space-time is nice and flat. Now from you also shine a light beam from C to D as well. But since well, space-time is curved, light would actually travel on a curved path from C to D. Now you can obviously guess that the distance from C to D would actually be a little longer than the distance from A to B. But we know that the speed of light has to be constant. For that, well, they reach each other at the same time, but we need to know that we need to assume, as per Einstein's special theory of relativity itself, that nothing can travel faster than light, and light speed itself is fixed in gravity, irrespective of your reference frame or perspective. So in order for light speed to be constant, we have to take some changes in the way that we perceive time. So we know that when speed is by time, so if speed needs to be constant and if you increase distance, time should also increase according to it. So what happens near a gravitational field is that the time has to be longer, which means time will run a little bit slower. Well, you might have seen this in the movie Interstellar, where Cooper and his team travel near a black hole named Gargantula, and they say that if you go to a planet which is orbiting around Gargantula, every hour that you spent on the planet will be equal to spending 7 hours on the Earth. Well, this is a direct consequence of the general theory of relativity. Now, that is even applied in general terms, like we think of it every day. Like for location systems like the GPS, you need the time to be exactly correct. In fact, the time at Wayanad is a little slower than the time here at my house. The time at sea level is a little slower than the time on top of the Mount Everest. The time on the surface of the Earth is a little slower than on a satellite which is orbiting around the Earth. So if you were to think of GPS, the clocks would actually run a little slower near the surface or on ground stations than how it does on satellites. So if you were to neglect or ignore this difference in time, the location that you get will be miles away from where you actually are. This thing has been beautifully explained in Dr. M.R. Shivaraman sir's lecture on GPS. If you haven't watched it, you can go and watch it from our YouTube channel or Facebook page as well. Now, we were talking about, what was it? Yes, GPS. Now let's come back to this gravity well concept. Well, when you have the sun, it bends space-time a little bit. When you have a more massive or a more compact object like a neutron star, the space-time curves a little bit more than how it would if the sun was kept at that place. Now, what if we have a black hole? Well, it would just create a huge well that it would almost be so steep that you can't climb over it. That is, nothing can escape this gravity well. Now, as I said, you need a critical velocity to stay in orbit or escape from this gravity well. So what happens when this gravitational force increases? Well, obviously the critical velocity required for you to stay in orbit would increase as well. What if the gravitational force is so strong that the orbital velocity is higher than the speed of light? Well, Einstein himself said that nothing can travel faster than light. If nothing can travel faster than light, then nothing, not even light, can escape from such a gravitational force. This bad boy, who ain't gonna care for you, is called a black hole. Now, let's go back to our second question. How are black holes formed? In fact, it is theoretically possible to convert anything into a black hole. You can be a black hole, I can be a black hole, the Earth can be a black hole, anything can be a black hole. In fact, if you compress anything into such a compact space such that the density is so high, the whole mass could actually compress in on itself and create what is called a black hole. This small radius that up to which you have to compress something so that it becomes a black hole is called the Schwarzschild radius, which is also numerically equal to the radius of the event horizon of a black hole as well. It is named after this man, this German physicist called Schwarzschild, who provided the first exact solutions to the Einstein field equations of general relativity for the limited case of a single spherical non-rotating mass. And the expression for the Schwarzschild radius is given by 2gm by c squared. Now, if you were to compress Mount Everest to the dimensions less than a nanometer, you would get a black hole. If you were to compress the Earth to the size of a peanut, you would get a black hole. But I would never fancy the idea of eating that peanut anyway. So as I said, it is possible to convert anything into a black hole, but it is really difficult to convert the Earth into a peanut because we don't have the technologies possible, and I really don't want the Earth to be crushed into a peanut anyway. But what about stars? Stars much larger than the sun. Well, they have much larger Schwarzschild radiuses, so radii. So you can compress it into a black hole if the situations are correct. So stars much larger than the sun can actually form black holes. But before we think about that, the first thing to understand is what is a star and how a star is formed. Well, what is a star? Well, we know that it is a massive body inside which there is nuclear fusion in the core, so that energy is released and it releases light and we can see it. That is, well, a star. But how, I explained of the term nuclear fusion, right? Yeah, nuclear fusion is basically when you fuse two lightweight nuclei like hydrogen, you get a larger nuclei. But when you measure the mass before the reaction and after the reaction, you understand that some of the mass was lost. Well, where is it? What happened to it? Well, it is converted to energy, which is according to Einstein's law of equation of the mass energy equivalence, E equals mc square. You can calculate the energy that will be released. In fact, there is another process called nuclear fission where you can like divide a huge nucleus like uranium-238 into lighter nuclei, so that some of the mass is lost and is converted to energy. You know that August 6th was Hiroshima Day, and tomorrow, August 9th, is Nagasaki Day, which is a cold-blood reality of how we use nuclear fission to, well, kill ourselves. But we have also been able to harness nuclear fission to produce electricity. But yeah, it is true that it produces harmful radioactive wastes. Nuclear fusion is in fact much more greener because it doesn't produce any radioactive waste, but we have not been able to harness it to produce electricity. But we have actually done it in, what do you call it, uncontrolled ways in some things like hydrogen bombs. So as I said, nuclear fusion to start, you need a high amount of temperature and a high amount of pressure. So how does a star form? Well, in things like nebula, the gas particles come together, they orbit around each other, then they aggregate into small particles, and then small bodies, and then into larger bodies, and then you grow in size and size and size. And when it grows in size, the gravitational force increases as well, and thus the pressure and temperature at the core will increase as well. And then when the mass of the star reaches a critical value, which is equal to 0.08, that is 8% of the mass of the sun, the conditions for nuclear fusion to start, for the nuclear fusion of hydrogen to start, is achieved. And thus hydrogen is fused, and what you get is an energy, an outflow of energy from the core. So you have gravity trying to compress the star, and then this energy that is released from nuclear fusion trying to expand it. So this tug of war between the energy released from nuclear fusion and gravitation, the equilibrium is what creates a star like the sun as we see it. But when the sizes of the star increases much beyond the size of the sun, well, there is an upper limit to how big a star can be because of things like photo disintegration. So what happens is that when you have really huge stars like BY Canis Majoris and things like UY Scuti and Stephenson 2b, the stars are not even spherical. They are like bulges. You have a very ununiform kind of a star. It's not even spherical. So we were talking about this equilibrium, right? So we know that hydrogen will not exist forever. Hydrogen will be exhausted. Then what do you do? How on earth can you give energy? There's no energy outside. The star will try to start compressing again. But when it starts to compress, the temperature and pressure increases inside the core. So what happens? Well, the temperature and pressure increases. So the conditions to fuse helium is achieved. Then they start fusing helium. So when helium is fused, you get a more amount of energy outside. So the star starts to expand. And then when helium is lost, well, the same process is repeated, and then you reach carbon, and then with a cycle of carbon, nitrogen, oxygen, and then you reach silicon, and then finally you reach iron. But there is a problem with iron. Well, iron is a very stable nucleus. We know that so far we've discussed that the fusion process was exothermic, that is, you got energy outside. But the fusion of iron nucleus is endothermic, that is, you will have to give energy, so you won't be getting energy outside. So well, there's nothing more to fuel the star, so well, gravity wins over it and gravity compresses it. Now at this situation we have three possible fates for a star. Now, if the star was a small star like the sun, well, as I said, it would expand to a red giant, and then if there is no fuel left, it would start to compress, and well, gravity tries to compress it to a tiny point. But then you reach a situation where the atoms and molecules, the atoms get really tightly closed packed to each other. But we know that the electrons will try to what do you call it, repel each other. So we know that electrons occupy certain energy states, and there are a limit to how much electrons that can exist in a given energy state. So if you try to compress them, well, there will be more than the ideal amount of electrons in that energy state, and thus it tries to repel. Well, just think of it, when electrons try to come together, they try to repel, and this repulsion causes it tries to balance this gravitational force. To put it in terms of quantum mechanics, it says, you might have heard of the Pauli's exclusion principle, which says that two electrons or two particles of the same spin cannot exist in the same orbital. Now, if this mass was to be compressed to a really tiny spot, the probability of finding more than one particle of the same spin at the same orbital will increase. So to stop that, to prevent that from happening, well, it will just repel each other. And this repulsion and this force just thus arising is called electron degeneracy pressure. And electron degeneracy pressure is what stops gravitation from compressing it even further, and the sun would form a white dwarf. Now, the sun would burn like this for another 5 billion years, and then for 3 billion years, it would become a red giant, and in like 8 billion years or something from now, it would become a white dwarf. But when the star is much more massive than the sun, the end is a little bit more spectacular. Well, you get a huge expanded star called a red supergiant. When they are even more larger, you get something called red hypergiants. Well, they expand to huge sizes, and then when there is no more fuel to start nuclear fusion, well, the star starts collapsing. But when the core starts collapsing, a shock wave as a reaction is sent outwards, which pushes the outer layers of the star in a beautiful, spectacular explosion called a supernova. You might have even heard that supernovas are even more brighter than the galaxies in which they exist themselves. Even supernovas are the reason why we find a lot of elements that we see on the surface of the Earth. And even these supernova remnants are what create a lot of other planets and stars and so on. But after that, you get a compressing core inside, right? What if the mass of the core was to be greater than 1.4 times the mass of the sun? Dr. S. Chandrasekhar, he was an Indian American mathematician and physicist, who said that this electron degeneracy pressure will only be able to well, stop gravity from pushing in to a single spot if the mass of the core is less than 1.4 times the mass of the sun. If it is more than that, electron degeneracy pressure will not be able to resist that, and the star would still go on to compress. And then it would form the electrons would fall into the nucleus and into the protons, and you would get a sea of electrons called a neutron star. And then the same Pauli's exclusion principle applies to neutrons as well, because two neutrons of the same spin are very unlikely to exist on the same near each other. So if you were to compress it even further, what happens is that two neutrons of the same spin, the probability of them existing nearby will increase, and to resist that, well, there is a more stronger pressure that tries to suppress gravity, and this creates an equilibrium state called a neutron star. You have to understand that a neutron star is not completely full of neutrons. The core is actually full of neutrons because electrons fall into protons and you get a huge sea of neutrons. Out of that, you get a mantle, which is made up of a mixture of protons and neutrons, protons and neutrons and electrons. And outside, you get a shell of iron. Now, the reason why this has to be explained this way is that, you might have heard about things called pulsars, where neutron stars spin so fast that they create huge magnetic fields, and for magnetic fields to set in, there has to be charges, right? So if the neutron star was completely filled of neutrons, that is, if it was chargeless, how on earth can there be, well, charge? Sorry, how on earth can there be magnetic fields? So to explain that, we say that the core is made up of neutrons. Outside, we have a mantle filled of protons and electrons, and outside that, we get a crust of iron. Now, what if this collapsing core was even larger? Say, we don't know the exact value, somewhat like 3.1 times the mass of the sun, or much larger than that. What would happen? Not even this pressure from the neutrons would be able to resist gravity. Well, gravity will win over, and it would just compress everything into a single point in space-time called a singularity. And then we get what is called a black hole. Now you may ask a question: if a black hole is only a single point in space, what is this huge black sphere that we see in this image? To address that, let's speak about the structure of a black hole. Well, as I said, the black hole itself is basically a singularity, which is a point of infinite curvature and infinite density in space-time, where all the mass of the black hole is found. Now, this glowing thing, this glowing disk that is seen around the black hole is called the accretion disk. What it actually is that if there is any star nearby, it would suck in the matter from the star, and the matter would start to revolve around the black hole. So they would collide with each other, there would be frictional force, and they would get heated up to millions of degrees, and they would emit light, and we see this glowing disk around a black hole. Now, when you travel towards the black hole, well, the orbital velocity increases until you reach a point where the orbital velocity is exactly equal to the speed of light. So what happens there? Well, there, photons or light wouldn't necessarily fall into the black hole, neither would they necessarily move out. Photons start orbiting around the black hole in this point, and this is called the photon sphere. Now, if we travel further inside, well, the orbital velocity would be larger than the speed of light, and well, nothing, not even light, can escape from it. So that is called a point of no return, and this is called the event horizon of a black hole. Now, what is inside this event horizon? Well, we don't exactly know about that. Now, we told you that light is not coming from a black hole, so it is invisible. So how on earth do you observe a black hole? Well, there are three possible ways of observing a black hole. The first is on how it influences the motion of other bodies nearby. So here you see in this GIF image a lot of stars and a lot of things moving around, possibly some kind of central point, right? This is actually a depiction of Sagittarius A, which is the center of the Milky Way galaxy. When we looked at Sagittarius A, we found out that there was nothing there. How on earth are all these things moving around such a point? How on earth is that possible? So scientists had to assume that there was a huge supermassive black hole, millions of times the mass of the sun, at the center of the Milky Way galaxy. And the reason why we can't see that is because, well, it is a black hole. There is another way to observe black holes, and that is when they emit gravitational waves. Well, you might have heard about electromagnetic waves and the electromagnetic theory of James Clerk Maxwell. Let me try to say that in another sense. Like, if you might have studied in school about the Rutherford model of atom, and one of the limitations was that if this electron was to move around, well, obviously it is getting accelerated, and so it would emit energy in the form of electromagnetic radiations. Thus, it would lose energy and just tumble back into the protons or the nucleus. That is not only true with charges. In fact, when bodies of mass accelerate, they also emit energy in the form of waves called gravitational waves. In fact, when I shake my hand like this, I am emitting gravitational waves. When I walk, I am emitting gravitational waves, because the space-time is actually, fluctuating when I walk, because I am having mass, right? But the problem is that my mass is so small that I would never be able to detect this small gravitational waves that I emit. But what about huge things like black holes and neutron stars? Even that, we talked about electrons going around and that they lose energy and fall into the protons or the nucleus. So actually the earth, when it moves around the sun, it actually loses energy in the form of gravitational waves, and it could in fact fall into the sun, but the mass of the sun and the earth are so small that they emit very small amounts of energy in the form of gravitational waves. And so you don't have to expect yourself falling into the sun anytime soon, because before that the sun would have actually died anyway. So we were talking about gravitational waves. So what if these bodies were having high amount of gravitational force, like well, neutron stars or black holes? Well, they have much larger gravitational force, and they would thus well, emit much larger amounts of energy in the form of gravitational waves. So they would start to circle, and they would actually come closer by emitting a lot of energy in the form of gravitational waves. If they were black holes, this process would actually be a little bit faster. In fact, when neutron stars collide this way, they could actually produce a black hole. It is also another way of producing black holes, because the mass of the core would increase when two neutron stars collide. So as I was saying, when we detect these gravitational waves, we could assume that they come from thus these kind of binary systems of neutron stars or black holes. Now, this was actually, we have previously sensed gravitational waves using the LIGO, or the Laser Interferometry Gravitational Wave Observatory, which is a series of observatories around the globe which have actually detected such gravitational waves in the past. Now, there is another way. We know that this accretion disk, which consists of the matter that is moving around the black hole, and since it is getting hot, it will emit light, right? So if we observe the accretion disk, we could say that maybe there could be a black hole. So for that, you actually need some star nearby so that the black hole can suck in the matter into it. So as you see, this image was captured by the Event Horizon Telescope. Actually, it was taken in 2017. It was released last year in 2019, and that is the first ever image of a black hole taken by humanity. And this is of the black hole at the center. It is a supermassive black hole, much larger than Sagittarius A star, which is located at the center of a galaxy called M87 or Messier 87. Now, you can see something like, well, a lot of people ask this question: why is it that underneath you have a yellow or white kind of a more higher frequency light, and above you get red shifted kind of light? Why is it that? The reason is that well, the black hole is actually spinning, and this accretion disk, or the matter in the accretion disk, is also, well, revolving around this black hole, and it is rotating in such a way that yeah, just think of it, the particles or the matter is actually coming towards us at the bottom and is going away from us at the top. And since you might have heard about the Doppler shift, the Doppler effect, when the source comes near the observer, the wavelength decreases and you get a higher frequency light. In fact, what we have observed is not white light. It is not visible light. It is actually a false image. The white light is used to show a higher frequency radio signal, and the red light is actually when it moves away from us, when the source actually moves away, the light or the electromagnetic radiation gets redshifted, and you get a radio wave which has a higher wavelength. So that is how you explain this complex color radiation that you see around this image. Now, this is a schematic diagram of the Event Horizon Telescope. It is actually a series of 13 radio telescopes that exist all over the globe. In fact, to observe something so far away, you need a telescope which is as large as the Earth itself. And well, building Earth-sized telescope is not something that the present economic situation would be funding for. So what they did is that they found an ingenious solution of placing multiple radio telescopes at different positions in the Earth's surface. And we know that there is a little bit of time lag, since light has a finite speed, so the time at which the light reaches different observatories will be different. So they had to minimize this difference in time, and they had to take this information together using a special algorithm in a correlator, and they well made this image of this black hole that we just see in the screen. Now let's take things a little bit more seriously. Let's start a trip into a black hole. Well, that is not a very good idea because you can't expect to come back. Oh, wait a minute, I have some problem here. Can you please hold on for a moment? My, you know, I'm losing a bit of charge on my phone. Perfect. Okay, now it's fine. Okay, now it's fine, sir.
Okay.
Okay, so we were going on a trip to a black hole, right? So yeah, as I said, it is not a very good idea because you don't expect to come back. But for the sake of humanity, for the sake of exploration, we are going to take that risk. But before that, you have to be careful in selecting which black hole, because it would be better if you select huge supermassive black holes rather than a smaller stellar black holes. There is a reason for that, which I will tell you later on. So what happens when you get nearer? Well, obviously you get accelerated. Your speed increases when you get nearer and nearer the black hole because you're being accelerated, right? So when you move nearer, your field of view becomes larger and larger, covered by black color. It becomes more and more black. And then you reach this position in space-time where the orbital velocity is equal to the velocity of light, or the photon sphere. So if you were to stay there for a moment and look at the side, you could actually theoretically see the back of your head, because the light from the back of your head would go all the way around the black hole and come to your eye. Cool, spectacular. Well, what happens when you go even further? Well, you reach the event horizon. Well, there is nothing we can do about that. We just go in, we can't communicate, but that's it. That's the end of the trip. But what would someone outside the black hole see when you're trying to fall in? They would not actually see you getting accelerated towards the event horizon, but rather they would see that you're becoming slower and slower and slower. You would slowly decelerate, and then you reach this point in space-time called the event horizon, where you just freeze all of a sudden. You don't move, you just freeze. And then the light from you gets highly redshifted and redshifted and redshifted until you just fade away. Well, they would never see you crossing the event horizon. Very sad. Now, what about the person falling into the black holes? Well, falling into a black hole is not going to be a very good experience, because scientists say that excuse me, Shajit sir, is there any audio problem right now?
Now it's clear. Yes, you just switch off one of your microphone.
Okay. Do you actually see my face? I doubt that.
Yes, we are seeing your lateral side, lateral view, not front view.
Okay. Now you can hear me perfectly, right?
Okay.
Okay.
But it's,
okay, now it's perfectly, right?
Yeah, it's okay.
Okay. So we were talking about well, yeah, how when you fall into a black hole, what would happen? Well, when you get near the singularity, the difference in the gravitational force on your head and your feet becomes so high that you would be somewhat like stretched. Well, this effect is called the tidal forces, because when there is difference in the gravitational forces on two different parts of a body, well, it would deform the body. If you were to fall feet first into a black hole, you would be just stretched like spaghetti, like how Dr. Stephen Hawking astronaut is being done. And this is not called elongation. Scientists call it spaghettification. And you would just be torn apart into the particles that make you, and it would be really painful. In fact, if you were to travel near small stellar black holes, what happens is that the difference in the gravitational force would be so high that you would be ripped apart even before you reach the event horizon. But when you take supermassive black holes, it would be much calm, and the difference in gravitational force on your feet and your head would not be that high if you were to take a supermassive black hole. So you would be able to cross the event horizon quite smoothly, unless you get fried due to the temperature around the accretion disk, if you don't get fired, well, you would be able to smoothly cross the event horizon. It would take a few more hours until, well, you will still get spaghettified. You would still die. Now, uh, what would happen when you move inside the event horizon? Well, we don't know what lies. We may think that there is a singularity where there is infinite curvature of space-time, but we don't even know how the singularity works. In fact, if we were to find how the singularity works, we might actually have to combine the general theory of relativity with quantum mechanics, and the theory has already been named as the quantum theory of gravity. A few people think it another way. Einstein's theory of general relativity provides a solution where there could be no singularity. It could be that things falling in will get spewed out from some other end, maybe in the same universe or even in some other parallel universe. Like you would get sucked into a black hole and you would just fall out of a white hole. Still, you wouldn't be able to return. This is, well, a wormhole. All of you know that. This kind of wormhole that which arises from Einstein's equation is called an Einstein-Rosen bridge. But it may not be possible to cross it, as it may take infinite amount of time to cross an Einstein-Rosen bridge, and they could even get a shut in the middle. But it may be possible to travel from one point to far away almost instantaneously, or even travel through time. Yet we have no observational data to confirm any of these hypotheses. All I can say right now is that if you jump into a black hole, you may not be the stuff coming out of it. You would just be dead. Of all that we've spoken, a little bit different as well. Here is another analogy for wormhole using a paper. So if this paper was to be straight, the shortest distance from A to B would be a straight line. But if we were to bend this, well, paper, you could actually go straight from A to B almost instantaneously. And is that possible? Well, yes, we thought that mass can warp space-time, mass can crush space-time, or mass can even tear apart space-time. So it is theoretically possible for you to travel from A to B almost instantaneously through a wormhole, even faster than light. That's pretty cool. But of all of that we've spoken so far, it seems that black holes are dangerous and we are always at the risk of falling into one. A lot of people think that if we were to change the sun with a black hole of the same mass, everything would get sucked into it. Well, there is nothing special that is sucking you into a black hole other than its gravity. Well, and gravitational force depends on the mass of the body as well as the distance between you and the black hole. So if we were to change the sun with a black hole with the same mass of the sun, well, all planets would actually feel the same gravitational force. You would only have the potential danger of falling into a black hole if you are 10 miles or 16 kilometers away from the black hole. But we are actually a comfortable 150 million kilometers away from the black hole. So you don't have to worry about this if the sun was to be a black hole. Even then, Mercury, which is 46 million kilometers away, would also not have any sort of problem whatsoever. Well, that is basically it with that. We're almost there right now. Time to address the next question. Will black holes live forever or will they die? It was a question that puzzled physicists around the world until 1974, when probably who was the greatest physicist of our time, Dr. Stephen Hawking, came up with this revolutionary idea that black holes can slowly but steadily fade away, slowly evaporating in the form of radiation called Hawking radiation. Until then, physicists thought that they only had some basic understanding and believed that black holes don't emit any kind of radiation. It all changed in the year 1974 when Stephen Hawking said, well, wait a minute, lol. Black holes ain't so black. In fact, black holes could emit radiation. He formulated this theory by combining the general theory of relativity of Einstein, which deals with the large-scale structure of the universe, with that of the smallest, well, yes, quantum mechanics. You might have heard about Jyoti Basusar's class on quantum mechanics, and I would like to borrow some things that he said and well, build upon that right now as well. Now, to understand Hawking radiation, we need to know about, well, probably the most difficult to grasp concept in modern physics, quantum fluctuations. Yes, the name seems a little out of the earth. This has been, in fact, observed to be true even. So, what are quantum fluctuations? Now, before we learn quantum fluctuations, we have to study a principle which is the basis of quantum mechanics, which is the Heisenberg uncertainty principle. Most of you may already know about that. It is given that you can never simultaneously predict the position and the exact momentum of a quantum particle like an electron or a proton or anything else. It is mathematically stated as delta x times delta p will be greater than or equal to h over 4 pi. That means if the momentum was to be accurate, excuse me, there is somebody trying to present. Please do switch off your presentation. Shadi sir, I'm going to present once more. Can you see my presentation right now? Hello?
Yes, Bharat. Yes.
Is my presentation visible for everybody? Should I like represent it once more? I think somebody presented it right now. Is it visible for everybody? Please do comment in the chat box.
Bharat, continue. I have done it.
Okay, sir. I think if somebody actually presents, then I will just exit out of what do you call it? Well, presentation. So you can you have to pin it once more. So if you haven't pinned it, I can try to do it once more. Is there a problem? Okay, that seems there to be no problem. Let's continue with that. If there is any problem for anybody, please do comment in the chat box. Varun and somebody else will clear that. Now, we were talking about the uncertainty principle. So if the position was to be accurate, the momentum would be very inaccurate. I think, sir, that is a problem with a lot of people. Can you please stop sharing and please do that one? Hey, sir. Sir, let me please do that.
So, you please stopping present your screen.
Mr. Please do stop presenting your screen. That is the problem. If somebody presents it, I just exit out of that, and you have to pin my screen, and only then will you be able to see that. And N square creations. Yeah, I'm trying to present it once more. You'll just see it right now.
Yes, Bharat. Yes.
Right. It has almost been more than 1 hour, right? I'll be closing in 15 minutes or something. Please do give me a little bit more time. So back to the Heisenberg uncertainty principle. Now, this is the way that we know about the Heisenberg uncertainty principle. Delta x times delta p greater than or equal to h over 4 pi. But this uncertainty principle of Heisenberg can also be applied to other complementary variables, complementary set of variables. Example, well, here we have tried to express it in terms of energy and time. It is mathematically stated as delta E times delta T greater than or equal to h over 4 pi. What this means is that the uncertainty in the energy possessed by a particle times the uncertainty of the time for which the particle inhibits that energy state is greater than or equal to h by 4 pi. So if one of them was to be found very accurately, the other would be very inaccurate. That is, if we know the energy of the particle, we don't know how long it has that energy. And if we know the time spent in that state, we would not know the energy of the state. It brings us to quantum fluctuations. Now, when the shorter the lifespan of a particle, the greater the uncertainty in its energy. So particles then, thus, since we don't know the energy of a particle, particles can just pop into existence from out of nowhere, and provided they exist for incredibly short periods of time. So if they can exist for really short periods of time, they can just pop into existence and, well, from out of nowhere. But they emerge as pairs. They don't emerge as a single particle. They emerge as pairs, as a particle and an antiparticle. And since they exist as particles and antiparticles, they are not real particles. They are actually virtual particles. If you, I'm not explaining that. We can try to do that if you want to in the question answer session anyway. So since they are virtual particles and since they are particles and antiparticles, this does not violate the principle of causality. In fact, quantum fluctuations can explain a lot of things that we see in the real world. An example is the Casimir effect. Have you heard about the Casimir effect? Well, it is a little tough, but let me try to explain it in a simple way. So Consider you have two thin metal plates placed at a very short distance from each other, say something like a nanometer. What you would see is that, well, these two plates would just be pushed together into one single piece. What force is causing it? How do they just come into each other and, well, just get pushed into each other? This cannot be due to, well, gravitational force. Neither can it be due to the electromagnetic force. So the reason here is that there will be quantum fluctuations nearby. So there will be more virtual particles on the outside of these plates, more than the ones that will be formed inside. So since there are more outside, the net force which is acting on these plates will be so as to press them together into a single piece. That is the Casimir effect, and that is how quantum fluctuations explains the Casimir effect. Now, we've said that virtual particles are thus formed everywhere in vacuum of space. Quantum fluctuations can happen, and particles and antiparticles can emerge out of nowhere. Therefore, empty space is not really empty. If it was empty, how can you get particles like that? So empty space is not empty, but rather it is actual substance itself. And this property of space is called a quantum foam, a sea of probability from which virtual particles are created and, well, destroyed. You know that a particle and an antiparticle, when they come together, they annihilate. Now, we've explained quantum fluctuations as to be of very tiny time durations, because when these particles and antiparticles are formed, they would just very soon annihilate each other, forming what is releasing energy or anything. So empty space is thus not empty, and therefore empty space has measurable energy. If there was no energy, how can particles just come out of nowhere? So this energy, which is embedded in the very fabric of space-time, is called zero-point energy. And this can explain the third law of thermodynamics. In classical physics, we understood that a system can never be cooled to absolute zero in a finite number of steps. So that is, complete absence of kinetic energy can never be reached. The reason is that there will always be a tiny amount of energy embedded in the very fabric of space-time, which restricts you from achieving absolute zero. Is the sound cutting out? Is there any problem? I hear from the sound. What happens?
No problem. You continue.
There was a problem with the audio. Okay, back to well, quantum fluctuations. Now, in, well, open space, particles and antiparticles are formed, and they would just annihilate each other, well, leaving nothing else. It would just, like, they come and they go. Nothing happens. But what if quantum fluctuations happen near the event horizon of a black hole? Well, things become much more complicated. So if such a quantum fluctuation happens near the event horizon of a black hole, like seen in this GIF image, well, one of those particles could actually fall into the black hole and the other would actually be emitted out. So it is actually like a negative negative energy is falling into the black hole and a positive energy is going out. So you can think of it another way. What if an antiparticle was to be falling in and a particle was to be going out? So the antiparticle would go in and annihilate a particle inside the black hole. And what happens is in the net effect is that, well, the mass of the black hole is lost, but we see that a particle is being emitted from the black hole. Even though it is not directly coming from the singularity, the net effect is that the black hole is losing mass and it is actually emitting some kind of particle. This is what Hawking radiation really is. But it is not clearly established how an evaporating black hole could look. We think that Hawking radiation itself contains highly energetic particles, antiparticles, and gamma rays. It is invisible, so you and I may not be able to see it at all with our naked eyes. But it is also possible that Hawking radiation might power a hydronic firewall, which could degrade the high energy particles and radiations to lower energy, which could make an evaporating black hole visible, making its end a little bit spectacular. Scientists doubt that a few observed gamma ray bursts may be a result of such decaying of black holes. But Hawking radiation posed more challenges, which led to probably the biggest paradox that exists today, the information paradox. Now, according to quantum mechanics, information cannot be destroyed. Now, to clarify, the information referred to here are quantum mechanical properties of everything in the universe. To put it simple, well, consider a sheet of paper. Well, you have a lot of atoms and molecules and things inside it. There'll be a lot of chemical bonds and stuff. So if you were to analyze it completely, you could understand what the nature of the paper is. So this data is basically the quantum information of the paper. So if I was to burn this paper, what would happen? Well, it is an irreversible process, so I won't be able to get the paper back. But if you take it in an isolated system, and if you, what are the gases emitted, the nature of the gases that are emitted, if you observe the residue that is left behind, if you calculate the temperature that has formed, if you calculate the pressure inside, and all these kinds of variations that happen inside the isolated system, I can combine all this information to find out that the thing that was burned was paper, because nothing other than paper will burn like paper. Like kerosene won't burn like paper. A plant leaf won't burn like paper. So if I collect this information, I can understand, I can go back and I can retrace back in time to say that what existed before was a paper. So this means that information cannot be destroyed, which is a fundamental concept of quantum mechanics. But as per the model that we've discussed so far, black holes could actually delete the universe. Now, suppose a star was to become a black hole. Well, we know that the whole mass would be compressed into a singularity, which is a single point in space of infinite mass or of infinite density. So we don't understand what star actually became a black hole. If something like I was to fall into a black hole, I would probably get ripped apart, and I would my mass would be added to the black hole. But you would never get information that I actually fell into the black hole, because my quantum information might just be lost. Now, as per the definition of Hawking radiation, as per the definition, nothing that enters a black hole can escape. So we know that in Hawking radiation, the black hole is actually getting evaporated. So, basically nothing that goes in can get out. And how, if the black hole just spontaneously gets evaporated, where is the quantum information that went in? What if I went in, and if I was to be evaporated, where is the information that went in? Where is me? Well, nobody knows. So scientists satisfied this frustration by saying that maybe we should think about the inside and the outside of a black hole as two different realms which cannot communicate with each other. We know that you cannot send a radio or an electromagnetic signal outside the black hole, because nothing can escape from it, right? So the inside and the outside of a black hole are two realms which cannot communicate with each other. So we can save the information that went into the black hole by allowing it to exist in two places, both one stuck inside and the other leaking out with the radiation. Usually physicists would say that you can have two copies of this identical information at once, but since the realms can't communicate, well, they kind of get a free pass. But I hear some kind of noise coming out. Is my voice clear?
Bharath, no problem. You continue.
But things got a whole lot complicated in 2012 when a physicist, Joseph Polchinski, and his colleagues realized that the paradox was a whole lot more difficult to solve. They imagined what would happen if you have two entangled particles, like particles that are quantum mechanically linked, and if you toss one of them into the black hole and kept an eye on the other one. But this would create a problem. By the very nature of the entangled particles, they must be able to communicate with each other. But if they were to exist in two different realms that cannot communicate, what is the point in speaking about quantum mechanical entanglement? That is a big problem. It is a big issue. It just violates the laws of quantum mechanics. Scientists thus came up with a revolutionary idea saying that you're not going to be spaghettified near a black hole. You're not going to fall in and you're not going to be ripped apart and become a part of the singularity, but rather you'd be incinerated, like you'd be set on fire or something. You'd just be incinerated near the event horizon. Thus, all your information would just be scattered, or they would just be bounced back. It won't just, it's like nothing could fall into the black hole. Nothing would cross the event horizon. Everything would be incinerated on the event horizon, and all the information and everything, all the particles and everything will be bounced back into free space. Now, thus conserving the information, and that's because there is nothing Now, why is it that you can't go beyond the event horizon? Scientists said, well, there is nothing inside the event horizon. There is no, black holes don't have a center at all. There is no singularity, and there is nothing inside this event horizon. It is just blank. But this is a little problematic, because if you were to think that way, the event horizon would actually be the end of the universe, because if there is nothing inside, if there is no space inside, the event horizon would be the end of the universe. And Einstein's theory of general relativity is torn apart by this concept of incineration at the event horizon. That was when Stephen Hawking, he returned once more, and he gave another impressive idea with a 2-page statement, which the entire physics community was completely perplexed. He said that both the ideas about black holes that we've just discussed so far are wrong. He wrote that there can neither be any singularities nor any event horizons. Instead, there are some things called apparent horizons, which store and scramble all the matter that gets stuck into it. This may solve the entanglement problem, as the particles can still communicate. It could even solve the information paradox, as the information is only scrambled and not deleted. So it is theoretically possible to retrieve it. But even then, without a singularity to create such a strong gravitational field, it still messes with general relativity. If you are scratching your head right now, don't worry. Anybody who hears this does the same. Nobody knows why Dr. Hawking proposed such a thing. And so far, it feels like, this is an equally problematic situation that we talked about before. For now, I leave you to decide whether you want to be spaghettified, whether you want to be toasted, or whether you want to be scrambled, or if you want to be, something else. But none of them feel to be appetizing for me. Anyway, that is it about black holes. Black holes probably ain't the end of the universe, and black holes ain't that black. But the problem is that we still know nothing about black holes. Everything that we know about are only theoretical speculations that it could be that. It could be possible that black holes don't exist at all. It could be, something like a simulation. What if we are living inside a simulation where everything that we see is being governed by someone else? Yeah, you could incorporate the concept of God, like you're in, something like a video game, and the person playing the video game is your God. So it could be possible that we are being toyed with. But even then, it gets a little spiritual, or probably it gets a little so awkward. So yes, black holes are very inexplicable. They are very incomprehensible. But if you have understood a little bit of that, and if you have had this idea of studying more on black holes, that is when I would be happy for being able to converse with you for so much time. Thank you so much. Thank you for hearing me out. Thank you so much. Back to Shajil sir.
Thank you, Varun. Today, thank you, Bharat. You crossed all the limits. You crossed the time, you crossed the limits of space, and you crossed the barriers which were exist in the minds of these the people who gathered here. That's why we are sitting here for 1.5 hours. That hasn't happened in these 12 weeks. That's why we have more than 100 participants, and all these force us to you to continue, and that's a blessing. I think all the people, all the scientists sit here, and if there is a chair in their mind, we can say it's education chair in their mind. Now you are there in their mind in that position. I can say it's not an exaggeration, and you proved that. And you have to travel a lot for our nation and for our fraternity. And we are so proud of you. That's the only thing I want to say. And we have eminent person from a physicist we got today to bless you. That is Dr. Shaji sir. And Shaji sir will speak, and he will fill everything about your presentation, wonderful presentation. I invite our distinguished Shaji sir to make a shower of blessing on you, and correct you and comment you. Welcome, Shaji sir.
Hello.
Yes, sir. Thank you, sir.
Is the audio okay?
Yes, sir. It's okay, sir. Continue,
Yeah,
please.
it was a great talk by Bharat, and congratulations. Yeah, I don't have words to describe that. It was really good. So, all the best for you. And the talk was really good. Maybe you can look at the questions and try to answer, and maybe I'll make some comments there if needed.
Our Babu sir says that he will face with the questions and these things. And I think after that we will get some more additions from his part also. Our students want to hear you. That's why that's the thing, sir. You can talk after you can choose the choice after this question and answer session. If it is so, let me invite Shoban sir also to add some more things.
Can you hear? Hello.
Yes, sir.
Hello.
Yes, sir.
Can you hear?
Yes, sir. Okay. Okay.
Okay. First of all, I congratulate Master Bharat for his wonderful presentation. And during the end of his talk, he posed a question. If I think what will happen to me if I fall into a black hole? Definitely, from your presentation, I can tell you that you will escape through the white hole with more energy, because knowledge cannot be annihilated. Knowledge is the power. So you have got that powerful caliber. So definitely you will escape from the realms of this type of problems. Then I have to speak something about the virtual particle. So virtual particle is a bit confusing concept in physics, especially in quantum mechanics. I have to quote one word from Richard Feynman, that if you think you understand quantum mechanics, then you don't understand quantum mechanics. This anecdote is most suitable for this type of exotic particle. The particle is nothing but a ripple in space-time. So if you're treating that particle as a ripple in space-time, that material view of particle will disappear. And this ripple can produce its own effect, its own disturbance. And that disturbance produced by a real particle is called the so-called virtual particle. For example, I'll show you one thing. Okay. Yes.
It's okay, sir.
It's okay. Can you see?
It's okay, sir. Yes, it's okay. It's okay. Now you please take your slide. That's only required.
It's not working. Some problems, technical problems. Okay. I shall continue.
The presentation is okay, sir. You can take the slide, sir. If there is slide, you can use it. It's okay. Presentation is okay now.
Okay. So, what is the difference between this disturbance and the ripple?
Shravan sir, your whole computer screen is being seen. Shravan sir, your whole computer screen is being seen, not the presentation. You are sharing the screen.
Something happened here.
Now the presentation has gone, sir. You have to represent it again. But the desktop was there. The slide hasn't come. That's why.
Here. So
if you are showing the entire screen, you should show just a window. Then it will be okay.
Is it okay? Can you see now?
No.
No. Okay, I shall tell you.
Okay. Continue.
Okay.
A ripple in a field that can travel smoothly and effortlessly through space is called a ripple. And that is a particle. And a virtual particle is a disturbance in a field that will never be found in its own, but instead something that is caused by the presence of other particles, often other fields. So this is the analogy that I can see, or I can say, when I am speaking about virtual particle. Ripple means it is just like an oscillation, something like an oscillation of a swing. The swing will be moving to and fro if you are pushing it. and it will have a natural period. And that kind of naturality is there for the particle. But if you are pushing this swing at a random fashion, the swing will begin to jiggle. And this jiggling is the disturbance. So that caused by some external agency, and that jiggling will naturally die out if there is no external agency. Similarly, if there is no cause for the production of the disturbance, which is called the virtual particle, actually that virtual particle will die out. So this is the simple definition or simple analogy that can give for virtual particles. Then there was a question like this: what is at the core? What is the state of matter at the core of a neutron star? At the core of the neutron star, scientists expect what we call quarks, which are the building blocks of fundamental particles like electrons, protons, etc. This is because the gravity is so strong at the center of neutron star that these protons and neutrons will be crushed into their building blocks called quarks. So this is only a prediction. Nobody knows what is the structure of neutron star exactly. Anyhow, I am not stealing the time. Shall just give one or two books for the students for their reference. One is The Black Hole War by Leonard Susskind, and the other book is Black Hole, a student's text, which is written by Derek Raine and Edwin Thomas. These two books deals this topic, which is presented by Bharath in a simple way without lucid mathematics. So with these words, I once again congratulate Mr. Bharath. Thank you.
Thank you, Shobhan sir. I think it's a real blessing to our Bharat. And we are again turning back to our distinguished guest, Shaji sir. And it's a question answer session. I think he promised us to deal with that session. And I think it's a good opportunity for our students to explore these great physicists. And I invite Varun to deal that question answer session and ask questions, make arrangement to ask questions direct to the genius. Shaji.
Hello, Shaji sir.
Hello.
Yes, okay. Bharat is there. I think.
Okay. Thank you so much, Shaji sir. Thank you so much, Shobhan sir. Shobhan sir, I actually loved your, analogy of comparing it with a white hole. Actually, it is people like you who, in fact, create such white holes, sir. Thank you so much for. In fact, a lot of things added to this presentation by Shobhan sir. A lot of things I added at the last moment when he told me, and I was very happy with the fact that he helped me a lot, and in fact, a lot of information that I incorporated into these things were from a lot of sessions that we received as a part of US Space Club and other education activities. So whatever I presented is not just something that I found out. It is because of all of you that I was even able to do such a thing. Thank you so much for giving me this opportunity. Thank you, Shaji sir, and thank you so much, Shobhan sir, for being my panelists. And thank you so much for everybody for hearing me out. And Varun, can you please make sure that nobody is presenting the screen right now?
Yes, no.
Okay. Thank you, Shaji sir.
Hello.
Now, there is something funny. Usually, I am the person who deals with the question answer session right now. But since but today, we have,
you can do it. You can do it. You are doing it very well. So you can answer the questions.
yes,
I can add some comments if needed. Okay, please go ahead.
I've been able to answer those questions.
Okay, sure. Go ahead.
Varnata, thank you. Over to you.
Okay, sir, can I ask the questions one by one?
Yes, yes.
Thank you, sir. First of all, Bharat, congratulations. A wonderful presentation by you. The way you presented the topic was awesome. And you touched all points like gravitational and force and black holes, King's radiation, and event horizon, especially every point over in your presentation. And wonderfully presented. I think you have become a celebrity by this topic. Congratulations, Bharat. And first question was asked by our chairman. What is the question is, can our Earth become a black hole one day? How big it would be? If so, how big it would be?
Varnata, can you please repeat that? It was not audible.
Can our Earth become a black hole one day? If so, how big it would be?
That is a very good question. Shobhan sir, can I please address that?
Yes, we can address.
Actually, as I said,
Already discussed that.
it's impossible for anything to become a black hole. All you have to do is that compress the whole mass into a very tiny point in space. So if you can compress the Earth into a size of a peanut, well, yes, you can make it a black hole. But do you have the technology that can compress the Earth into a black hole? Well, that is not something that we are sure about. So if you do have the technology to compress the Earth that way, for a time, we will consider that it is not possible to make the Earth a black hole.
Shobhan sir, please switch off your audio. Your audio is on.
I can supplement. Okay.
Yes, sir, sure.
Audio is on. Here, can you see it?
Yes,
can you
sir.
hear?
Yes.
Yes. Okay. I can supplement that answer.
Okay, sir.
Here, gravity is produced by the mass of the gravitating body. So, if F has got enough mass to produce such a gravity or such a great gravitational force or larger gravitational force, definitely it can become a black hole, because it should crush into the dimensions of a peanut if you want to convert that into a black hole. So there is not enough matter on Earth to become a black hole. That's what I could say. Okay, thank you.
Okay, so can I move to the next question? Okay, sir, thank you. Next question is by Abhiram. Is there any chance to conversion of a neutron star into a black hole?
Is that for me?
Yes, sir. Is that is for the entire panel? You can answer the question.
Okay, I'm not sir anyway, Varnata. So yes, it is possible for you to make a neutron star a black hole. Well, Shobhan sir already said you need to be able to compress that into a tiny space. So for that, you need a very high amount of gravitational force. So the it became a neutron star in the first place because there was not enough gravitational force for it to compress it into a black hole. But it can actually become a black hole if all of a sudden this neutron star was to gather in size, and if the mass of the neutron star was to be increased by some way, you can get a black hole. For instance, if two neutron stars were to collide, it could create a black hole. You may have read about things like kilonovas, when two neutron stars orbit around each other, and when they merge, the overall mass would increase, right? So sometimes the mass would be more than the critical amount of mass that is required for it to become what is called a black hole. So if you can add the mass of a neutron star by some way, yes, you can make it a black hole. Like if it collides, yes, obviously it can become a black hole. I don't know if there are any other ways, Shobhan sir, Shaji sir.
Yes, colliding of neutron stars, there is a possibility of forming the black hole. But scientists now think that the heavy metals like gold, platinum, uranium are produced by such collisions. The disruptions or the strong forces required to form such large nucleus are obtained in such collisions. Usually, if there is a white dwarf around this or orbiting this neutron star, it can swallow matter from that white hole, and as you said, its mass can increase, and finally it may become a black hole. I think Shaji sir can explain more about this. Okay, thank you.
Okay. Actually, there was a case of kilonova detected, I think 2 years back, by gravitational waves, and it was well studied, but people are not sure whether a black hole was formed. So that's a possibility. Two neutron stars, binary neutron stars, fusing together to become a black hole. Another possibility is of a neutron star and a black hole merging to form a black hole. So there are different possibilities. Yet another possibility is that some matter from nearby stars fall into a neutron star and exceeds the mass limit of a neutron star. It becomes a black hole. So there are different ways in which a neutron star can become a black hole, but we don't have clear evidence of such black holes. And there are cases of supermassive black holes. We really do not know how they form. One possibility is that many different things join together to become supermassive black holes. So the answer is yes, it is possible that a neutron star can turn into a black hole. There are different ways it can be done.
Okay, so thank you. The next question is by Febin Firshad. How is it white hole possible? He asked two questions back to back two questions. I will ask those two questions. One question is, how is it white hole possible? And what makes a white dwarf into a dark black dwarf?
I think Shaji sir can explain that.
Okay, let me try to answer the first question. See, white holes are a theoretical possibility. To think of a black hole and just take all those equations and do a time reversal. That is, instead of t, put minus t. So you'll get another solution, which you can call white hole. It will have properties the opposite way. Like black holes can absorb things from outside, but things cannot come outside things cannot go out from a black hole. In white hole, it's the reverse way. That white holes can emit things, but cannot accept things from outside. This is a theoretical possibility, but we don't have any experimental or observational evidence to support the idea of white hole. some people sometimes think that when you get something like
Chandrasekhar, your voice is not clear.
see, when there are some cases like gamma ray burst, which cannot be explained by other means, some people propose that it may be a white hole. But we don't have solid evidence for the existence of white hole, but it's a theoretical possibilities. And we don't know any mechanism by which it can be produced from evolution of ordinary stars or motions of planets, galaxies, etc. So that's the answer to the first question. Second is how white dwarf can become a brown dwarf or a black dwarf. See, white dwarfs are dead stars in the sense that nuclear fusion almost stops there. Okay, it's when nuclear fusion stops, then you say that a star is dead. Just like when you say that the heart stops, a human being is dead. So people say that when the nuclear fusion stops, a star is dead. But the dead star contains a lot of energy. And the white dwarf will be small in size, but it will have a lot of energy, and it will not be a good conductor. The material inside a white dwarf will not be will keep emitting some radiation, but it can go on for billions of years. But at the end, because of conservation of energy, it will lose all the energy. And if it loses the energy, it cannot radiate. Then it become brown or black. And okay, that's it. So basically, because it will keep losing energy. There's no mechanism by which white dwarf can produce energy except say contraction, but that will not contribute to much energy. So once it loses a lot of energy, the temperature goes down and it becomes brown or say black. I think it's okay. It's over.
Yes, sir. Okay. So before the next question, I just want to say one of our students core team members should take the link for the quiz for this webinar from our students core team group. I request Adil or Sriram to take that link and to post in the chat window. Please do it. And so next question is by Navneet Shajil. Is it possible to detect the gravitational wave generated by Earth and the Sun?
In principle, it should be possible, but practically it is not possible because the rate at which it will emit gravitational radiation will be extremely small, and we don't have any method by which it can be detected. So with the present technology, we will be able to detect gravitational radiation produced by cataclysmic events like merger of two black holes or merger of a black hole and neutron star or neutron star, white dwarf. So only by collision of compact objects we'll be able to detect with the present technology. But theoretically, it should be possible. Practically, it will not be possible in the near future. Is that okay? It's over.
Okay, sir. Okay.
Varun.
Yes, sir.
Varun,
Yes.
Can I interrupt for 2 minutes?
Yes, sir. Sure.
Students can still ask questions. I just wanted to say very few things. One is that, today has been a very brilliant day by a brilliant talk by a shining star. Both this brilliant and shining is used by you, Varun, for describing your friend Bharat. And that has turned out to be very true as Bharat finished his presentation. Excellent presentation. So here, I just want to record how Bharat came to our space club and, how he shaped up so well. He made a presentation in one of our space camp in the university on how to improve the propulsion system of PSLV. It was well received. Of course, not he alone, he and Varun together as a team made the presentation of efficiency improvement of the propulsion system of PSLV, and it got the appreciation of the present director VSSC, Dr. Somnath. And he comes from that kind of variety of brilliant student, and I am extremely proud to see him presenting so well today. Another second thing that happened today was Mr. P. Padmanabhan, a flight dynamic expert of ISRO, who deals with orbits and other things of ISRO satellites. He called me up. We all call him lovingly as Papan. And he called me today and said, see, I am sorry, I will not be able to listen to Bharat. He was feeling very frustrated because he had some other urgent thing to attend to at this time, and he was feeling so bad that he is not able to listen to a student, Bharat. But he knew Bharat very well. He has been seeing him in several space camps. So these two incidents I just want to bring to the notice of not only Bharat, but his student friends and all of us who are present here. See, we are passing through a very, very bad time. Bad times is a part of our life. Of course, nobody think of this kind of a pandemic or the kind of a landslide that happened yesterday in Munnar, or the air accident that happened in Calicut. Of course, bad times we have to face. And that is a challenge to the humanity. That is a challenge to all of us. We are feeling very sad for it. So I am talking about the challenge because our students have taken the challenge of meeting their future. They know the future is not that bed of roses. There can be problems. So they have taken the route of how to face the challenges. And this is one such challenge faced by students like Bharat. They know how to come up well in life, how to fructify their student life, academic life, how to come to a career, what are all required, what is the learning, what is the a career, and what is science, and what is beyond earth, all these kind of dreams. The dreams that make them awake, as Kalam said. They are keeping awake with the dreams are bothering them, and they are keeping awake to fulfill their dreams. Bharat, you had an excellent job, and I wish you all the very best. And all the students who are listening to him should try to get some message out of what he has said today. And I am very, very happy that today we have got very eminent personalities, great achievers, veterans, scientists, eminent teachers, exceptionally able people, and very, very able students. So that is and we had touched our viewership today, 123, and that is something, a record which Bharat has set. So thank you very much, Bharat. It has been an excellent day. Even in the midst of these sad days, I enjoy today seeing you talking so well. Thank you very much, Bharat. Thank you, Shoban sir and Shaji sahab, for coming and blessing our Bharat and the rest of students. Thank you.
Thank you, good sir. Thank you for your words. And can we move to the next question? It's by Hardikas Nair. And his question is, are white holes and wormholes are the same thing?
No, they are not the same things. They are different things. As I said earlier, white holes can be considered as a sort of time reversal of the black holes. Wormholes connect two different space-time points, maybe two different black holes. So these are two different things. Wormholes and white holes are completely different things. Over.
Okay, sir. Thank you. Next question is by Dakshina Anand. The question is, how are black holes connected to wormholes?
First, let me say that black holes really exist. We have a lot of evidence for the existence of black holes. But so far, there's no evidence for the existence of any wormholes. So wormholes are hypothesized things. And in principle, there can be a wormhole connecting two different black holes. But some people think that this will not be stable things and will collapse. So some people even theoretically say that there cannot be stable wormholes. So no evidence for that. So wormholes connects black holes. That's a possibility.
So next question is just based on a paradox, I think. The question is by N Square Creations. The question is, what is dark matter?
Okay, dark matter is something that exerts gravitational force, but not visible to us. I mean, when I say not visible to us, it cannot be observed by any kind of telescope, visible telescopes or infrared, UV telescope, radio telescope. No telescope is able to see it, but it exists. We know about its existence because of its gravitational effect. For example, you think of a galaxy. We can measure its mass from the way the stars move around. So from that, you can calculate the gravitational force, and indirectly, you can calculate the mass. Another way to calculate the mass is to count all the stars from their brightness, etc. You make an estimate of their masses, and then add all the calculations do not match. And you add all the visible mass, that is only, say, sometimes 10 or 20% of the mass that you make, you calculate. Dark matter. We know what it is, but the only thing we know that it exerts gravitational force.
Okay,
it's not, okay.
So the next question is by Question Bank. Master Abhiram, he is one of the most active, most enthusiastic student of UL Space Club. He has a lot of questions. Do you want me to read that one by one, or can I ask it all together?
One by one. I will not be able to keep track of all questions. You may ask one or two together.
Okay, sir. The first question is, can we send a spacecraft into the ergosphere and get it out from the ergosphere?
I really do not know the answer. Okay, I can't answer it. I don't have.
Shobhan sir or Bharat, any of you can answer?
It's a conceptual thing presented here. It's just like gaining energy from the black hole. So, if a flight is going into the ergosphere, and after entering into that ergosphere, by some mechanism, if we can trigger that out of the ergosphere, then surely that gain enormous amount of energy from the black hole, and it can escape. But it's only a concept. There is no evidence for that. Okay.
Okay, sir. So the next question is, if we send some electromagnetic energy, into the black hole, it will become an object with a huge amount of energy. Can we convert the energy into our needs?
If you send electromagnetic energy into a black hole, it will just absorb it. For example, if light goes into a black hole, it will come out. So you don't get any energy back. It goes into the black hole. That's what usually happens.
Okay, sir.
So except Hawking radiation. We are not talking about Hawking radiation right now. So if electromagnetic energy, whether it is light or in form, it will just fall into black hole and will be lost forever. That's what Einstein's theory would say.
Shaji sir, isn't it possible to extract energy from black holes by using the conservation of momentum, like when you use gravitational slingshots and things like that. Isn't it possible to extract energies from black holes in that way?
No. See, if it goes into black hole, it's lost. Like, except through Hawking radiation, it will not come out.
Sir, like if it was to get near the black hole.
To describe a slingshot, you don't have to consider whether it is a black hole or another object. If it goes by if it passes by a distance, whether it's a black hole or another object, gravitational force will play a role. But to get more energy by sending light at a black hole, I don't think it is practical. I mean, it will change momentum, okay, but that will not. I mean, I don't know how to get any energy from that. I don't have anything else to add.
Okay, sir. Can I move to the next question?
Sure.
Can you please describe about quarks?
Okay. Quarks are constituents of particles like protons, neutrons, ions, etc. For example, a proton is made of 3 quarks, 2 up quark and a u quark, and a neutron is made of 1 u quark and 2 d quarks. So there can be large number of there are actually a large number of particles which are made of quarks. So all these strongly interacting particles are made of quarks. See, there are 4 different types of fundamental interactions: gravitational, electromagnetic, and then 2 different types of nuclear forces, weak and strong. So all particles that show strong interactions are made of either quarks or anti-quarks, or a combination of quarks and anti-quarks.
Okay, sir.
But one more thing, let me add. You cannot have free quarks. Quarks always comes in group. For example, proton and neutron comes in as 3 quarks. Pions comes as a quark anti-quark pair. You can't have single quarks, free quarks. That's not possible.
Okay, sir. One more question regarding quark. It is how does the particles in neutron star change into strange quark?
Sorry, I didn't understand the question.
How does the particles in neutron star change into strange quark?
See, quarks do interact between them, so that's possible. But I don't. I have not read about that. Neutron stars quarks in neutron stars turning into strange quarks. See, if a strange quark is produced, probably an anti-strange particle also is produced. So nuclear interactions can produce strange particles. I mean, strangeness is just a property of a type of quarks. Quarks, there are different types. One particular type of quark is called a strange quark. If that is what you mentioned. It doesn't have the usual English dictionary meaning there.
It's a quantum stage.
It's a quantum stage. Yeah, it's a kind of a flavor of quarks. It's a type of quark, strange quark. Just like U quark, D quark, C quark, T quark, there's S quark. That's called a strange quark. There's actually nothing much strange about it. It's, for some historical reasons, it was called the strange quark. Don't confuse the dictionary meaning.
Okay, sir. Sir, can I move to the next one? It's a question that I selected from a discussion in chat window. When Bharat's talk was going, there was a few discussions went on in the chat box, and I selected one question from that discussion that many of the students should know what the answer is. The question is, how many dimensions that string theory demands?
Okay, that depends on the string theory. Some string theories propose 10 dimensions, 11 dimensions, etc. So you can have a string theory in any dimension in principle, but earlier there were some way in which they used to select certain dimensions. So string theories are now not in fashion. I mean, though there were a lot of attempts on string theories, they have not been very successful. So in principle, you can have string theories in different dimensions. String theories in 10 dimension is quite usual. I mean, many people used to work on that.
Okay, sir. We know that a black hole really attracts everything around it by its gravitational force, gravity. And Ashin Hari has a question about it. That question is it possible for a black hole to eat an entire galaxy?
See, if you are far away from a black hole, its gravitational force is quite similar to gravitational force of a star. So it's not only when you go very close to a black hole, it will show very strange behavior. Otherwise, you can assume that black holes have gravitational force which goes 1 by r square. I mean, just like the way sun or a planet attracts. So even if there's a black hole, it may not eat up the whole black galaxy. We are reasonably sure that there is a black hole at the center of our galaxy. Okay? And it's actually matter is falling into that galaxy and it's getting bigger. But we don't expect that it will eat up the whole galaxy in, say, 10 billion years or 20 billion years. That's very, very unlikely, because only if things fall into black hole or fall close to black hole, it will be able to catch up. Because the gravitational force is almost same, just like a big object when it's away from it.
I think Bharat has already answered that question when he discussed about the formation of black hole at the location of sun. It will not affect the orbital velocity or orbital parameters of the solar system, except that the planets will not get any solar radiations. He has already answered the question. It will not eat the entire solar system.
Yes, Sovan sir. Actually, I did.
Okay, sir.
Varnata, can I add something?
Yes. You.
I would like to repeat what I said over there. Actually, a black hole, the only thing that a black hole does is that it attracts you towards it. So there is nothing special attracting to you towards a black hole other than its gravitational force. So even if you have the sun, or if you have a black hole of the same mass, there will be no difference whatsoever in the gravitational influence it exerts on, say, Earth. Because as Shaji sir just said, it depends on the mass and the distance between them. So I had mentioned that if you have a black hole with the same mass of the sun at the center of the solar system, there will only be strange behavior if you get as near as 16 kilometers or something near the black hole. If you are 150 million kilometers from the black hole, you have no sort of, you don't have to worry at all. The only thing, as Shobhan sir said, is that there will be no solar radiation you will receive. So, well, obviously there will be no photosynthesis. You will die. And if there is a possibility for you to live, well, probably there is a good chance that you'll be able to sleep for much more time than usual.
Okay, Bharat. The next question is also from Hardik. And can I ask the question? Can I move to that?
Sure.
What happens to all the energy and matter that enters a black hole? I think that's answered in early question. Can you please repeat the answer, sir?
Maybe Bharat himself can answer its question.
Yes, sir.
Bharat,
what happens to matter falling in a black hole, right?
Matter and energy.
Okay, so that is a very puzzling question. Before that, we actually thought that if black holes were to exist, every sort of energy and matter that was to fall into a black hole would actually get spaghettified, and it would add to the mass of the black hole. That is what we thought so far. But it was when we thought about the information paradox when things actually started to differ a little bit. Because if this, if the matter and the energy was to be lost forever into the black hole, it violates the principle of quantum mechanics that information has to be conserved. So that is why we came with new explanations that maybe the matter and energy falling into it will not add to the mass of the singularity, but rather what happens will that it will get incinerated at the event horizon itself. And then Stephen Hawking said that maybe, well, that is not the possibility. The information or anything that falls into it will get scattered around the event horizon. A lot of, you might have heard of something called the holographic principle, where the information must be stored on the event horizon in the formation of in the form of two-dimensional information and things like that. Well, it is actually right now we can assume that maybe it would fall into the black hole and it would actually add to the mass of the black hole, but it could be false because we don't know what is inside a black hole. I didn't mention about a lot of things, like there is something called an inner event horizon in a black hole, but that is speculation because we don't know what is inside an event horizon. So that is a very difficult question to answer. But these three things that I mentioned in my presentation are some probable situations, but even then none of them could be true. Probably it would be none of them, probably even that well, black holes aren't black holes. Black holes are something else. I think some of the experts can add on that something. Shaji sir?
Yeah, you have put it clearly. See, according to Einstein's theory of relativity, if it goes in, that's it. You don't get any further information from it. But quantum mechanics makes it slightly different. And we don't have a good theory where quantum mechanics and general theory of relativity is combined. So there are some speculations. So you have to deal with these paradoxes like information paradox, and then issues like principles like holographic principle, etc. So from general theory relativity point of view, once it goes in, it's locked forever. I don't have anything more to add. I mean, you have to wait for some time. That you may get an answer within the next few years. I mean, you may get a better answer. But,
yes, sir. Maybe some of these people who have listened to our presentation would be the people who will solve it. Who knows?
Yeah, sure.
Maybe the speaker also.
That is a very small probability, but as you said, quantum mechanics and the whole world is governed by probability, right, Varnata? So there is a probability.
Okay, well, can I move to the next one by Abhiram US?
Sure.
If black hole grows, then how it will die?
That is a good question. That is something that I did not address. The only problem with black holes like evaporating away is if there is no matter being added to the black hole. Like if a black hole is alone, all alone, home alone, then obviously there would be nothing to add to the mass. So the net effect, it would always be losing energy and mass in the form of Hawking radiation. If Hawking radiation is true, it will always be losing energy and mass. But if mass and energy is keeping on being added, then the net effect would be like it is increasing in size. So it completely evaporating off is only when there is no matter being added into it.
Okay, Bharat. One more question is from Abhiram US. The question is, what happens when an object having mass equal to Sun enter our solar system?
That I have already explained twice, I think, Varnata.
Okay, Bharat. Next question is from Ashwadi OT. The question is, if the Sun were a black hole, would the energy we receive change?
Well, not exactly. As I said, the Earth and the planets move around the Sun because of the Sun's gravitational force. And we said gravitational force depends on what? Well, the mass of the Sun and, the distance the planets are from the Sun. So even if you replace it with something like, a black hole, there wouldn't be much of a difference, but there will be energy difference, that is for sure, because stars emit energy in the form of radiations, right? So we will not receive the electromagnetic radiations, the light that is coming from the Sun, if you keep a black hole there. I don't know if there is any other sort of difference in energy that you're going to receive from that. Shaji sir, Shobhan sir, anybody?
Yeah, you have answered it well. If sun is replaced by a black hole, gravitational force is not going to change. So Earth will keep moving around sun, but of course we will not get sunlight. So there will be energy problem. But Earth going around sun will continue. No problem.
Okay, sir. The next question is by Dakshina. Most probably that's the last question that I selected, and I have two questions more that I just kept in a waiting list. And if there's a short of time, yes, we are facing short of time, then we will end up with this question. And the question is by Dakshina. And what if we fall into a spinning black hole rather than a static black hole?
That I think should be answered by the experts. In fact, I didn't address that. I should have addressed that, because when black holes start to spin, well, it actually drags the space-time around it as well. So there's a whole lot of weird things that happen when black holes spin. So I think it is obviously sure that the expert will be able to tell much better than me. Shaji sir?
See, it also depends on at what speed it rotates and things like that. We don't have any observational data from spinning black holes. But as Bharat said, there will be a dragging of the thing. Anyway, if you actually fall into a black hole, the main thing will be what is the mass of the black hole. If it's a supermassive black hole, I mean, very large black hole, then ironically, when you cross the event horizon, you may not feel any big thing happening for you, okay? Because the change in gravitational force will be very small if it's the massive black hole. But it's a small black hole, you will feel it, because there will be what we call tidal force will be larger for a smaller black hole. So I can say that it will be smoother if the black hole is a really huge, massive one. And rotation, what difference it makes, I'm really not sure. I have not worked on it. I have not thought about it.
Yes, sir. I've heard that if the black hole was to be spinning, then the effect of spaghettification and all these kinds of things will be very weird. It would be pretty much like falling into a grinder, rather. So I would prefer falling into a non-spinning black hole. Yeah. No, I would not prefer falling into any black hole, but if I was to fall into one, I would definitely not fall into a spinning black hole. And sir, I've heard these things about, well, spinning black holes only lead to Einstein-Rosen bridges. Can you please explain that?
No, I have no idea. I mean, spinning black hole, how it's related to wormholes, I have no idea. Sorry, I don't have much to add to this.
I think Shobhan sir had unmuted his mic for something. He wanted to say something, I guess.
Theoretically speaking, at the core, the singularity will be turning into a ringularity, a new concept that is coined in. Instead of a singularity in a spinning black hole, that singularity will also be rotating, so it is called singularity. And I think using that ringularity, such a thing is possible theoretically. That's all.
Okay, sir. The selected questions are these are the selected questions. And one more thing, I just want to get an answer from you guys, the panel members, and Bharat. The question was discussed on chat window. There is a detailed discussion on chat window why few students are asked that question: what exactly gravity is?
And that is a very good question as well. I think it is better the experts address it, because all I know about gravity is that general relativity says that gravity is only an interaction between mass and the space-time fabric itself. But when you come to quantum mechanics, you try to explain forces in terms of particles, in terms of virtual particles that Shobhan sir actually talked about. We say that gravity is actually caused by a virtual particle called graviton, and this virtual graviton is what causes something to move around the sun or something like that. And when you observe gravitational waves as the form of real gravitons. So maybe our experts can talk a bit about particles as well. So you may address that question a bit better.
I think Dr. Shajisar is worked on a lot on field theory, so he can definitely speak something about that.
See, what I can say is that physicists are practical people. Okay, I mean, when you make models, you look for you look at experiments and you have explained things. So basically, it's experimental physics, and people are practical. So, for example, when Newton wanted to explain motions in solar system, and when he derived this formula like G m1 m2 by r square, he assumed the sun to be a particle, earth to be a particle with some masses and with the distance r. Then you get a very simple model, and that is good enough. But when you want to describe, when you want to discuss tides in earth, you cannot consider earth as a point. You have to consider earth as a sphere, and then you can explain it. And then when you want to discuss some other things like precession of equinoxes, then you cannot take earth as a perfect sphere. You have to consider that earth as a shape which is slightly different from a sphere. So you make that model. So this is the way physicists approach things. So what I'm trying to say is this: when you want to think about, say, an apple falling from an apple tree, or you climbing a tree, you don't have to consider gravitons or space-time geometry and things like that. It's good enough to use Newton's laws, and you think that just to take classical mechanics, and you assume that the earth is attracting the apple by a gravitational force, and the force is depends on mass, and you can take the force to be mg. That's good enough. Okay. But when you want to consider like a bending of light or a black hole, something like that, definitely you have to take general theory of relativity. And even then, you don't have to consider gravitons and things like that. Gravitons, etc., will come to play when you maybe have to think of nonlinear effects or strong regions where there's a strong gravity and the gravitation. Gravitational waves, something like that. So far, we don't have found any experiment in which you have to consider gravitons to explain that. So gravitons is a good concept, and just similar to electromagnetic field, you can think of gravitational field and quanta of gravitational field as a graviton and things like that. But practically, you don't need it for kind of everyday physics. So it is depending on the context. When you want to discuss quantum gravity and things like that. So when you go very close to a black hole, you don't have to, Newton's laws is not sufficient. So physics people are practical. What I mean is when you want to discuss ordinary things like motions in earth, things falling or going up, you consider it as a force, gravitational force, and you just stick to Newton's approach. That is good enough. If you don't want to do it that way, you can, of course, take Einstein's approach. And if you take Einstein's approach, this will come as a limit. This is not just about the gravitational force, electromagnetic force also. It could be possible. It is because of some intrinsic geometry in some internal space. There are attempts like that, what is called the Kaluza-Klein theories, etc., which try to combine Einstein's theory of relativity and quantum electrodynamics into a single theory or using some geometrical model. So it gets redefined. So what you call force will become something else. But from a practical point of view, or for a practicing physicist, you take either approach, saying that gravity is a force to discuss certain things, and you go beyond that to discuss other things. This is true about many other things. Like, for example, when I discuss, say, aerodynamics, I don't have to consider air as consisting of molecules and etc. You have to consider air as a continuous matter. And when you want to discuss ordinary optics, you can take glass as a continuous thing with some refractive index. You don't have to consider molecules and atoms and fields and things like that. So again, it depends on the context. So there are the same things you can consider in different ways, depending on the energy scales, depending on the length scales, and depending on the context. For example, you consider Earth as a inertial frame of reference if you don't bother about the effects of rotation of Earth. But if you want to send a rocket, you have to consider the rotation of Earth and consider it as a non-inertial frame. So basically, it depends on the context. So you can throw away Newton's theory of gravity and say that I don't need Newton's theory, Newton's concept of force, etc. I can just rely on Einstein's theory. That's good enough. Similarly, you can even throw away classical mechanics. You can just consider quantum mechanics and say that in some limit, from quantum mechanics, you get classical mechanics. So this is a philosophical point of view. So from practical point of view, you can choose what you want. It's easier for you to do calculations, etc. That's all that I have to say.
Okay, sir. Thank you. Now we crossed it. It's nearby 5:40. We seated we attended the webinar for 2 hours and 40 minutes, and it was a wonderful session. Thanks to Bharat and thanks to panel members. Sreejith sir, please, over to you.
Yes, really, it is a wonderful session. They already stated that we crossed all the limits because we have around 44, more than 40 people gathered here. The science enthusiasts are there. They are enjoying these things, and we are exploring our distinguished guest, Dr. Shaji sir and Shobhan sir. It was a real blessing. As our Kuti sir is also blessed our Bharat for his things, and already the comments are there even in the all India level. Bahya Gaisha group, the Bharat rocks in the groups, and everybody is commenting on his things. I think the YouTube, we have YouTube streaming, and YouTube is there. All these program is recorded, and that will be available to a lot of people. I think a lot of people will see this definitely. And it's our closure time, and we exceeded all our limit. and it's time, and we have the UL Space Club. It's coming under the ULCCS, and we are planning the EDU project, and all VIP is nurturing these scientists. And one more thing is that by looking these questions arising here is a good sign for this UL Space Club that all the students, the participants are motivated more, and they will also want to be like Bharat. And a lot of students want to be like Bharat, and he will be a role model to our students also. And that much enthusiasm is aroused among our students. And it's a closing hour, closing moment. I invite T. Damodaran sir, the coordinator, Vagbada the Jew project, to make his vote of thanks. And before that, I think one more thing may be added from our part, our chief patron, E.K. Kuti sir. Kuti sir,
please. Time is already overshot. And what you said, our objective of the space camp is being met, in a good measure through this kind of things. So we should be happy that the space camp is reaching its targets and aims. It's a nice thing. Now, one thing we have missed, we have not mentioned about our quiz here. Please say what's how we are, as usual. Please make a mention about it, about the quiz, and then vote of thanks, please.
Yes,
yes, sir. We have posted the link already in the chat window. The link for the quiz I have already posted in the chat window by Adil and Sriram. And the quiz will be active. Link will be active after this webinar. And the question is regarding this session. the topic of this section. The questions are taken from that topic, and you all of you should attend the quiz. And the prizes for the winners. The first person who send the answer to correct with his details to your space club through that link. And all the best to all participants. And over to Shejit sir. So it's time for vote of thanks, I think.
Okay. Thank you, Varun. And it is a great, it's a lapse from our part before about mentioning about the kiss, because all the actors, all the person behind them were the actors now, and that's why I just made some message to Varun and Bharat, and I didn't get that. That's why it's not mentioned. And usually we have a UL Space Club quiz, and it is sponsored by Center by Nurture. And
Sir, just a minute. Can I interrupt?
yes.
We just wondering that Bharat has the result with him for the presentation competition. We have already announced the result of Monday quiz competition, and now we have the result of presentation competition. I think Bharat have that, or if he is not able to present it, okay. He said that he don't have that. Okay, let me present the name of the winners. Just a minute, sir.
Before Bharat taking, we can declare the next week program. Next week we have finished 12 weeks here. We are it's a 12 years 12 episode is a great deal for us, and we are so proud in this achievement. And we are able to continue this. Next we have Dr. Sundarajan. He will speak on. He's a person from ISRO, and he'll speak on space technology. And after the next coming 22nd, we have an exclusive Malayalam webinar that will be dealt by the renowned writer C. Radhakrishnan, and he will be there, and some Malayalam literature persons also will be along with him. We can wait for a exclusive Malayalam webinar on 22nd of this month. Varun?
Okay, sir. Sir, can you hear me?
Yes, you can declare it now.
Okay, sir. The winners for the Monday presentation competitions of UL Space Club for senior category, first prize goes to Navneet S and Febin Firshad. They shared the first prize, Navneet S and Febin Firshad, and the second place Niharika P, and third place Joy Shibu Joseph, and special mention to Abhiram TP and Parvati Suryasri. For the performance, they performed really well, and they get close marks to the winner. And for the junior category, the first place goes to Amina Lanika, and second place goes to Gautam Sreejith. The third place goes to Krishnendu TN. The more details of the winners will be announced through our Facebook page. We just declare the name of the winners now, and we will contact them directly. And please watch our Facebook page. Please visit our Facebook page for more details about the winners, and we will declare the winners.
Okay, congratulations to the winners, and I invite Damodar sir to make his vote of thanks. Sir, please unmute your mic. Damodar sir, unmute your mic. Mic is not unmute.
Okay.
Okay, it's okay, sir.
Now, hello. Good afternoon, everybody. Today, the 12th webinar became a remarkable one in this series. Hello, Bharat. You have done a very good job. Excellent. Your presentation is excellent with high energy and enthusiasm. First of all, I congratulate you for the very informative and wonderful speech you have made. I'm proud to thank you honestly and wish you a bright future. Our honorable panelists, Dr. Shoban and Dr. N. Shaji, supplemented and supported Bharat very well. I extend our sincere thanks to Dr. Shoban and Dr. N. Shaji. I thank the eminent persons like Dr. Rangarajan, Dr. Jyoti Basu, Dr. P.J. Bhatt, Dr. Jairam, Dr. Shaheen, Dr. Sujit, Jairam, etc. for participating this seminar. Participating in every seminars and last seminars, all the last seminars. I extend our sincere thanks to all the participants of this program. Finally, I thank E.K. Kutisar, Schedule Master, Master Varun, Master Adil Krishna, Master Sriram for conducting this webinar very successfully, and I thank all the participants and Bharat once more. Thank you all. Okay.
I think, okay, thank you.